بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, in the previous lecture we have talked about an introduction to predictive modeling, and we have mentioned that predictive modeling is basically dealing with the optimization of a function that we call a loss function, and we use techniques like a gradient descent based on the data that we use. We are in the context of supervised learning where we have input and also the output. So we're going to try to find a model that will map to the best possible the input data into their output, and use predictive modeling where we are not able to write a function manually like we used to do in traditional programming to convert the input into the output, because usually these problems are very complex and non-linear and require advanced techniques in order to make the mapping between the input and the output. And the function optimization, so the function that we deal with is called the loss. Okay, we try to minimize the error. We've mentioned the example of predicting the house prices based on the number of rooms. And one of the possible ways to model the number of rooms with the prices is to use a linear regression. It's basically a line, okay, with two coefficients, A and B, or beta and W, that we try to find in order to map the input into the output. And we talked about also that every time that we train a model, we're going to find a particular loss. And if we do multiple training, we will find different values of these losses. What is the distribution of these losses? If we increase the number of trainings? Normal distribution.
So every time we do a test,
yeah,
the loss will decrease.
Yeah, so these losses will be random, and you will follow a random, a normal distribution with a mean and a variance. Of course, if the variance is very high, it means that there is no confidence about the expected value. So we need to do several iterations until we minimize the variance among different iterations. And this is based on the central limit theorem. Yes?
The model, predictive model, has a prediction rate of like specific rate, even if you do a multiple tests and it doesn't change. Where is the problem? How to increase percentage?
Sorry?
Prediction rate, like a prediction rate.
What is the prediction rate?
Like how
We have error, we have loss, or accuracy. What do you mean?
This loss.
The loss, okay?
Yeah. It's, like it stops on a specific rate, doesn't change. How to make it more accurate?
Yeah, the range is, when you do multiple iteration, according to the central limit theorem, you're going to have, the variance is going to be smaller, okay? You have seen when you talked about the central limit theorem, when we increase the sample size, okay? So the curve will be sharper. It means less variance. It means more certitude about the mean, okay? And this is why we try to do multiple iterations. And today I'm going to illustrate this. So we talked about the expected risk, which is the risk if we do it for an infinite number of iterations. And the empirical risk is actually the average value of the losses that we can get over multiple iterations. So I would like to illustrate this concept on a simple example of linear regression model. And in the meanwhile, I will introduce also several concepts related to Python programming for predictive modeling. So we're going to learn many things today. So here I will import libraries. Of course, you already know about NumPy. sklearn, this is scikit-learn. It's a library that contains several machine learning algorithms. So in our case, we will work with linear regression. We will take a simple example, as you will see later on. We're going to train models. So train, test, split. When we have a large data set, we need to split it into a training sample and a testing sample. So the testing will not be used in the training. It will be used later on to test the model on a data that was not seen in the training. And this is part of, is our model general or it only fits to the training data? This is one of the things. We will discuss this a lot later on, but just a brief introduction to this concept. So mean square error, you already know. We're going to use this metric to calculate the loss between predicted values and actual values, as we have seen. And matplotlib, you already know it's for plotting the graphs. So here we're going to do a very simple example. I'm going to use a linear function with known parameters. W is equal to 2, and the bias B is equal to 1. Okay? So let me introduce some terminologies. Okay, so we're going to talk about W is the weight and B is the bias, okay, which is the offset. So look at this example. I'm going to create like X values, and for every X I will calculate the ground truth, which is 2X plus 1. So I know the ground truth relationship. And then I will create another data set where I'm going to add a noise, a random noise, to the ground truth. So our data set will be X and Y values such that the X will contain a noise. واضحة الفكرة؟ So I will have a data set with noisy data, okay, X, Y, and I will try to find the line, the prediction line. So my prediction line, ideally, it must be to X plus 1. But now I'm going to add the noise in order to try to find the best fit. So I'm not going to make it perfect. It will be easy to do it for a perfect line. Okay, so you understand now, this is our X and this is our Y. And yeah, so we're going to generate X and Y, and this is the true label. The true label. Okay. So let's look on how, let me now generate a data set with a sample size 50 and a noise level 1. And let's look what happens. This is a visualization. Let me make the plot smaller, 5 and 3. So look at this. What do we have? We have the regression line, which is the ground truth. I know this in advance, but in reality, you don't know this in advance. We try to predict it. And this is the noisy data. So I'm going to use this noisy data, which is X and Y, to try to predict a relationship. Now, if we consider this as a scatter plot, we can observe that there is a correlation. There is a strong correlation here. So we can infer that there is a linear relationship. Now, let's assume I increase the noise to 3, for example, the noise level. Look at the data scattering. Of course, here, the loss is going to be certainly higher, okay, than if I make a perfect zero noise. So that's 100% correlation, you know. When the correlation is 100%, I can find a loss equal to 0. But in reality, I'm going to have a noisy data. So I try to find the best fit. What is the lowest error possible, okay, of the model that will represent the best fit for this data? Yes?
How to know what noise level does that take?
You don't know, now because I know the ground truth. This is a simple example, just for teaching and education. But in reality, when you have a data, you don't even know whether you have a linear regression. Okay? So linear regression, this is an assumption if you can see that your data, now, for example, if I remove this line, imagine that you have a data like this, and I say, make a predictive modeling. Maybe the first thing, okay, I can see that there is kind of pseudo-linear relationship. Let me try with a simple linear regression model. And based on this, you're going to find some losses, some errors. You will estimate the inference error later on your real data. If you say, that's acceptable, you can use that model. If it is not acceptable, no. Maybe the relationship is not purely linear, so I need to use more sophisticated technique, maybe neural networks or SVM or other techniques for regression. Okay, you see what I mean? Now, because here we start from a simple example when we know that we have a linear regression with some noise. Of course, you can see the impact of the noise if it is very high. Okay, it may impact whatever you do. The best fit model is not going to be perfect or zero error. So we will tolerate some errors in any case, but this error should be acceptable for the use case that we talk about. Now, the second function is about train and evaluate. So here, what we will train. So first of all, I'm going to take the data set and split it into two parts, one for testing and one for training. Usually there are different ways on how we can split. If I have a large sample, I can split it 80% for training and 20% for testing. Okay. If it is extremely large data, I can take even 95% for training and only 5%. I need to put sufficient number of unseen data to test the model over these data, because later on the model will be trained for the training data, but you don't know how it's going to behave. Okay, maybe your loss is small for training, but it will be very high for testing, so your model is not general. Okay, I need to find another way, and this is why we use testing. And this is linear regression. So linear regression, basically it will have random values of W and B. So in the beginning the losses will be high. And using gradient descent, something we're going to learn in detail later on with convex optimization, it will try to minimize until the loss becomes small. Okay, and finally it will return the mean square error. So this is a vector, which is the predicted y. Okay, it will predict every y values, and later on it will calculate the mean square error for this vector and this vector, which is 1 divided by n, the sum of each element. Okay, because this is a vectorized version of the model. Okay, any question here? Yes.
X-train will X test هي الانبوت والواي train Y test هي الاوتبوت.
Yes. So here we have X train. This is the training data set. Testing data set, X input features. This is the training output. I know the training of the output and the training in the input. So I will calculate two losses, the loss of the training and the loss of the testing. Let's make some examples, no problem. Okay. And this is a function that will plot the models. It will make plots like this for different cases. Okay. So what is our objective now? Is to calculate the generalized loss. Now, let's try with a simple example. I didn't put it here. Let's create a data set using this function. And then I will train the model. I will call this function. And this function will return these values. The test size is what? So the test size, yeah, it's a percentage. مثلا, I will put only 20% of the data for testing. Okay, and let me print the loss.
What's the size of the data?
Okay, look at the loss here. The size of the data is 50. And I will train the model X and Y, train and evaluate. It will return the training data set. Okay, and this one is what? So it will return the loss for testing. Let's calculate also the loss for training. So it didn't calculate the loss for training. I can do it here. So this is a testing loss. Test loss. Okay, I don't have the predicted here. So we can calculate. Let me make some changes. Test loss and the train loss equal X train and model. No. Because yes, it's not xtrain and model dot and y train. Okay, yes. So this is the train loss, and then we will have the test loss. So I will add here train loss and test loss. So let me print now. Print train loss شوفوا الآن train loss it's even bigger. Now later on we talk about overfitting, underfitting, so there are explanations. Let's increase now the sample size. Yes? Hmm? It's not always. Look now, when I reduce the noise level, the training is better. Okay? So later on we will have a lot of details. If the training accuracy is much higher than we say it's overfitting. It's fitting more the training data. If it is the opposite, we say it's underfitting. What does it mean? The model is very simple. It doesn't capture all the issues. Look now, the problem of having the training accuracy smaller is when we have a lot of noise. Let me increase the noise. When I increase the noise, or noise equal to 2 like it was, so sometimes the model is too simple. I mean, there is a lot of dispersion such that a simple line doesn't capture effectively the pattern. Okay? This is simplistic modeling. Maybe we need to have polynomial or some more complicated scenario. These are just marginal. We will talk about them in details. Yes?
Can you print the line here?
Yeah, I'm going to print, yes. Okay, let me make plot. I think I can plot it here all together. Plot. Plot model fit. And complete. Okay. So look now. This is the training data. This is the testing data. Let me just make it smaller. 6, 4. Do you understand the concept now? We're going to have losses. 2 here, 6 here. Now, this is normal. It was trained on this data and less for this data. Look at the testing data is a little bit far because it was not part of the sample that was used for training. It is unseen. Okay? And the model was more fit towards the data that is used for training. And this is what we call overfitting. It overfits the training data. Okay? In some cases, because this is random, let me make 50 here. Look, the training loss is higher. Like by coincidence, the data in the test was closer to the line. This is by coincidence. Okay? But less for the training. And in this case, maybe the training model is just too simple to model all the nuances of the pattern in the training. These are many difficulties that we face at daily basis when we train models. The two disasters is underfitting and overfitting. We want to have the accuracy or the loss pretty much the same for the train and for the test to see that our model is good and general. Okay? Is good when the training loss is small, is general when the test loss is similar to the training loss. It makes sense, right?
Yes.
Okay.
So,
Yeah.
how are we going to improve the model using this?
What do you mean?
Our main purpose is improving the model, yes?
Yes.
How is this going to help in improving the model?
It's not improving. You make a visual, you make an observation now. It's up to you to decide whether this is a tolerable loss or error or not.
If it is not,
Huh?
if it is not,
Maybe you change the model, maybe you increase the data set, maybe you change the parameters. So there are many ways on how to improve. So the first thing that we think about is to increase the data set. Now, look, if I increase the number of samples, I will have smaller losses in general
it's similar.
because the noise level is high. Let me make a lower noise level. You know, when you have a noise level is high, you cannot have lower than 3. You know, it's already too noisy. Okay? So the final accuracy is not only based on the accuracy of the model, but also how noisy is your data. If your data doesn't have pattern, I mean, if I chose a large noise, you don't have pattern. You know, you don't have correlation. You don't have linear correlation. Now we talk about linear correlation. When the noise increases, the linear correlation will be smaller. It's not like when we have 100% of correlation, it's like we have 30% of correlation. 30% of correlation means whatever you do, a line will not fit the data pattern. So it means that your model still is wrong. You must have something different to capture the pattern. Okay? So this is the idea of a pattern. Any data, we try to capture, look, this data looks very complex, but it has some kind of pattern. Now we guess that a linear pattern could make a good fit, but to which extent? Okay, 0.9 seems fine here. Okay, because I increased the data, so there is better convergence. Yes?
So here المعادلة تبع y equal to x plus 1 and 2 هي الويت.
احنا الآن we started from a known ground truth, which is not the case in reality. Okay? احنا we know the ground truth. What is the ground truth? It's 2 and 1. W equal 2 and B equal to 1. Okay? But in general, we need to make inference. Okay, we need to predict what is the best fit. Okay. And, okay, model.fit. And let's see the model here. So our model, it's a linear regression. Look, the coefficient of the model is 2.004. It's very close to our original one, right? Okay? And there is also model dot coefficient dot fit intercept. There is the intercept, which is the B parameter. 0.9, close to 1. واضح؟ And we know the ground truth. But because the data is noisy, we're never going to have the ground truth exactly. Even 2x plus 1 is not going to give probably the best fit. Yes?
So how can we choose the line? يعني what should we do to get a perfect line?
This is convex optimization. How we get this line, we're going to learn techniques. There are techniques based on machine learning, techniques based on linear algebra. But for now, we want to focus. Whenever I run an experiment, I have a loss. Now, what is our topic? Empirical risk. Now, you understand that when you change any parameter, you will have a different loss. Even if I don't change the parameters, look, I will run for the same ones. Will I have the same thing?
No.
It's different. Which one is correct? So now I have random losses. And to calculate the empirical risk, let me do the experiments thousands times. I will have a normal distribution of these losses, and then we get the empirical risk, which represent kind of a general understanding of what looks like as an error in average. Yes, and then.
W طلعناه 2.01.
Yes.
يعني طلعناه by convex optimization.
Yeah, of course, there are, in linear regression, we can do convex optimization, and also there are other techniques based on linear algebra. It's like a system of equation system.
نستخدم numerical analysis.
Numerical analysis, yes, numerical analysis is one of the ways to solve a linear regression problem. Okay? وفي الماشين learning أيضا باستخدام الجريدينت descent, which we are going to learn. You're going to learn how to build it. الآن we can use it. It's there. لكن what's behind? How it's able to optimize these weights. Okay? Now look, if we start the model in the beginning, if you start the model in the beginning, like this, So this model will have random numbers. Okay, it still doesn't even have any value. It will start something random. Okay, now if for example I will run, look here in the train, there are some parameters. I don't know if we can run the number of. So if here we are using the default values of training, but we can specify how many iterations, we can specify some parameters. If I train for only one iteration, it's not going to give me a good value. Okay? واضحة الفكرة الآن؟ Okay. So what I want you to understand is that training a model will not give you, usually what students do, or even researchers, they train the model. My training loss is 0.88 and the test loss is 1.0. I would say this is not correct. Do it again. You do it again. And you find a different one. Which one is more correct? Okay? This is why we need a confidence interval. Okay, so the empirical risk, it will give you an average value with some variance that will give you kind of confidence. And we don't do this only in machine learning. We do this in any kind of stochastic simulation or stochastic experiment. When you have random outputs, you need to average these random outputs and calculate the confidence interval. And you know in advance, according to the central limit theorem, we're going to find a variance that will represent the disparity between these average values. واضح? Okay. And now you understand why we had to go through this theoretical foundation to understand how to manage your experiments. Okay? As an engineer, you should not only just make experiment for, even now in the project, when you do predictive modeling, you need to have result consistency. You need to talk with confidence. Okay? Maybe you have some outliers that provide you a low training loss and you are fine and happy. You go to deploy it outside, it doesn't work as expected. So you must always have a systematic way of thinking about how you manage your machine learning projects. واضح? Okay. So, and this is a very simple example. Of course, in reality, the models are much more complex. So we have more urgency to follow these rules. Yes?
How big is the confidence level in our model?
Now, this is one experiment to show how things works and to calculate experimental analysis of linear regression parameters. So I'm going to use different sample sizes, different type of noise levels, different test sizes, and different type of number of iterations. So I'm going to do the same thing for different hyperparameters. This is how we usually can draw the average empirical results. Okay. Yeah.
If we have a low test loss but a high training loss, is it positive thing or what?
Sorry?
If we have a low test loss but a high training loss, how can
Yeah, this is what we call underfitting. And we usually interpret this as the model is too simplistic to capture the patterns of the training data. There could be many issues. There could be the problem of the model, the assumption that you've made on the model. It can be a problem about the selection of your train and test data. Maybe your test data, just by coincidence, was better fit for this model. This is why one of the ways we try to even swap what is training and what is testing. There are many ways on how we can do that, cross-fault validation. Okay, yeah.
خلينا نقول صار في راندوم اكسبيرمنت والمين حقه كان برا الكونفدنس انترفال بدينا نبرمج ذا الشيء يعني نسوي له ديسكاونت ولا نعدل عليه.
Yeah, now look what I'm doing. Because I don't have any trust of any of the values that I get, I'm going to create several experiments. Every time I'm going to calculate a loss value, and I will append it to an array. Okay, look at this training loop. For number of samples in sample sizes. Here, this is a for loop. I will go through all the sample sizes. And then I will go through all the noise levels. واضح? What I do? I generate a data set with a certain sample size and the noise. How many variation I will have? 1, 2, 3, 4, 1, 2, 3. 12 variation. واضح? For every sample size, I'm going to run data set with these noise levels. شفت الآن I work on generalization. Okay? Then I will increase the sample size. And I will do that for all noise levels. So I'm going to explore the dataset space. Okay? I'm not going to work into only one particular type of distribution. So I need to make sure that the dataset distribution is large enough to capture all the different patterns I can see in reality. That is not part of my training. واضحة الفكرة؟ Okay? And this is in simple linear regression problem. If you do, for example, computer vision, you need to make sure that the distribution of your images is large enough. What does it mean large enough? أخذ صور فقط من PSU وضربت model. Your model is perfect for PSU environment, but will not be perfect if you go to the desert, because the landscape is different. So what you will do, the picture that you take here, they will have a similar type of distribution. There is green trees, there are buildings, but if you go to another one, the distribution of pixels will be completely different. So in order to get a general model, you need to capture from different areas. Okay? And this is why when we train a model in Europe, if you want to apply it in Saudi Arabia, it may not work as precisely as it was in Europe, because the features here are completely different. And this is one of the things that we have worked on in research, is called domain adaptation. You have a model that works on a domain, and you want to adapt it to another domain because the distribution of the data is not the same. Shift to the end, we talk about simple things, but we talk the same language even in a more complicated scenarios. So always think about your data as a data distribution. The distribution of your data here is different if I change the noise level. Okay? So now our issue here is try to explore the different possible spaces of the data set in order to have the most general model as possible. And for everyone, I'm going to create a data set, I'm going to train my model, and then I will append to the loss a dictionary with the number of samples, the noise, the test size, and the loss. واضح? So running this loop, I need اوكي يعني غيرت شيء. هذه الان عندنا train loss and test loss، ولازمني نغير هنا، خليها هذه loss للتست ونزيد عليها train loss, not to make too much difference. وهذه عندي تست loss. واضح؟ ايش الاشكال الان؟ شوفوا الان. This is one model based on noise 0.5 sample. Then it creates another model. وكل model it has an MSE. Look at this MSE here, 0.3. The noise is higher, MSE is bigger. Okay? And then MSE is even bigger. Number of size is small. The noise is 2. Okay, so there is a relationship between the number of size. Now it's doing, I show you all the models. Maybe 12 models will be running, and you can see the impact. So later on, at home, you can play with these values. Okay, and check. Look at here, the MSE for sample size and too much noise. Okay, it's 3.8. And now we can calculate the empirical loss. Just running these cells. So the average here, I'm going to take all of them, calculate the average, and I can say in average, I will have an empirical loss 1.6. Of course, it's better here to also find the variance, because the variance will tell me the discrepancy. Okay, I had some losses between 0.2 and other losses at almost 4. So I want to see what is the range. Okay, so most likely, in most of the case, the highest probability, the risk will be around this value, but still it can go plus and minus. How large is going to be? It depends on the normal distribution, which is captured by the variance. Okay? And here you can see also some other plots. Okay, look, this is the impact of the noise. Plot risks, let me plot the risk. I put this 5 and 3. Look now, you will see nice results. This is the sample size and the empirical MSE. So we can see that in general, when I increase the sample size, the MSE in general is smaller for all scenarios. Okay, only 1.5, ولما only 20, above 175. The error, the mean square error. شوف impact of noise. When noise is 2, the MSE in average for all scenarios is around 4. When you have low noise, you have better fit of the line model. It means the linear model is good when the patterns are correlated. Okay, when the points are correlated with each other. And here with the noise, so I'm going to lose a lot of MSE. Okay, these are the main findings. Okay, and now I hope later on when I talk in the lecture about the risks, the loss, you have everything clear in your mind. You can, I sent you now this notebook. Please try to work with it, try to change values, make observations. This really helps. And whatever I used here, it's the same principles in any training of machine learning model. Okay, it's only the model that will change, but the principle is the same.